I am disabled to
Oh, sorry.
share my screen.
Great.
Um,
Can you try it again, Donny?
oh yeah, it's good. All right. So, why can I? Okay. Hi guys. So today I'm going to present about my current work with Hugh and Simon about the progressive evolution of thrust fault topography in the frontal Himalaya. And first of all, uh, where does it hold? So my study area is located within the sub-Himalaya. So that is the frontal range of the Himalayan range. It is defined with the MFT on the south, it should be shown here, and the MBT to the north. So in between these delineated area, there's a two thrust fault. And to be exact, so one of them is Churia Range, which is located uh, southwest to the Kathmandu. And we have Dandua Range further to the west of Nepal, and the Mohan Range in Dehradun, India. So what we are actually trying to do, we're trying to quantify the topographic characteristics of four locations. So the Churia Range will be divided into two parts across these topographic ranges generated by fault propagation and fault band fault in the sub-Himalaya. And we use this location as a record of the progressive evolution of topography to provide a first order tectono-geomorphic model for the evolution of fault and thrust ridges in the sub-Himalaya. So why are we doing that? So approximately, so like most of the shortening from the collision between the Indian plate and the Eurasian plate is accommodated within this part of Himalaya. So it's in the sub-Himalaya. It represents the southernmost propagation of crustal shortening of the range initiated during early Quaternary times. And we're trying to understand the interaction between the topographic growth of these structures and the channels that are sourced at the drainage divide of the ridges respond to uplift. So how we're going to do that? So to achieve this, we present the total shortening across parts of these ranges. So first of all, we're going to make a balanced cross-section of these four locations in the sub-Himalaya. And we are also using the topographic matrix, which is the KSM, the normalized channel steepness, channel concavity, and also the location and the magnitude of nick points, which are derived from the LSPLSR 12.5 meter resolution DEM using the integral method, or so called chi from Perrin and Royden, using this equation. And we're also trying to explore the potential role of grain size in river channels uh, using a backscatter radar analysis technique, which is recently being published by Printon and Bookhagen. So, uh, in a nutshell, what does the chi do to a river profile? So it actually change the river profile, which normally looks like this, into this. So it changed the dimension of the distance into a chi, and the slope or the gradient of this chi is the channel steepness function. And to uh, to locate or to identify nick points in the in our channels, we use segmentation of this KSN, yeah, we're using Boris methods here. So it detects a change in KSN values, and if we have a sudden drop in KSN, it will mark as the midpoint. And we're also trying to use the best fit concavity identification. So we are trying to look for the concavity of each basin from all these channel in this range using the collinearity of the chi. So if the if the basin has an has a proper concavity, it will show a collinearity. So, for example, what's a collinearity? So it's that's where the trunk channel and the tributaries are aligned with each other. So if you look at here, some channels are below the trunk channel, which is showing that the concavity is too high here. But it's almost collinear here in upstream, so which means that the concavity match in this part of the channel. And this is the geological map, which we uh, made based on previous studies. So these are for the Churia range. This line here correspond to a cross section later. Uh, Here we have a thrust fold to the south of the range, and also an anticline to the east. And for the Dunwa Ridge, we're going to focus on this part only because uh, this this part uh, the the arrangement of this range is perpendicular to the shortening direction, which is the same as in Mohan range and the Churia range. And if we're well, I mean, if we're going to look at the eastern part of the Dunu range, it will have a more like parallel uh, direction to the shortening direction. So we're going to just only focus on this part so we can compare to another ranges here. And this is the geological cross-section that we uh, made from the previous studies. So we have the West Churia range, the Eastern Churia range, the Danwa and the Mohan range. So the Mohan and Dandwa range is entirely taken from a previous study, which is from Huson and Powers and Barnes. But in the Western Churia range, we infer the the structure stratigraphic from the stratigraphy of the Siwalik, which so if you look at here on the Churia range, it's gradually exposed to to surface. So in this part, it's only it's the upper Siwalik exposed to the surface, and it's gradually like exposed to the east, and we have lower Siwalik on the east. So we think that uh, the uh, the structures, the fault are propagating in that section. So this is based on Sapi et al. 1992 on the development stage of fault propagation fault. And this one is so we built this cross section mainly from the data from Lave and Avak and some measurement of the dip using the topographic. And oh yeah, from if you look at if we're if we count the shortening amount from west to East Churia to Dundua Range and Mohan Range, we can see that the shortening in Western Churia Range has the has the lowest shortening, and it increased to the East Churia Range, and the Dundua Range on the other hand has the highest shortening from all of these range. And so the figures on the left hand side is the mapping of the channel stiffness across these ridges. We can see that in Churia range, it is somehow higher at the western tip of the range. Well, when we look at the east, it's generally lower compared to the western. And in and the Dunwood range has the highest KSN index from all of the ranges. And if you look at the Mohan, the KSN distribution generally constantly distributed along the ridges, along the ridge. And to make the observation easier, I've plotted the median of KSN in each on each these basins to a function of KSN and distance along the ridge. And we can see here that the Western Churia uh, has a increase of KSN values to the west. Well, the with the mean of 20.79, and the eastern part of the Churia range is lower with the mean of 13.46. And if we look at the Dunwood range, the mean for the KSN is 31.73, and the Mohan anticline it has the mean of 17.75. And okay, so this is the mapping of the nick point and the concavity, channel concavity across these ranges. So if we look at the nick point mapping here, we can see there are alignment of nick points everywhere. If we look at the Churia range, we have an alignment to the south of eastern Churia range over here. And we also have an alignment to the south of the western Churia range. But the north flank on Churia range it has a stronger alignment nick point. And if you look at the Tundra range, it also has the alignment feature of nick point here, both in the north and to the south. And if you look at Mohan range, it has a really strong nick point alignment to the south of the range. This is the best fit concavity for all of these basins in these ranges. If we look at the Churia range, we can see that the concavity is almost uniform between the north flank and the south flank in this part. But if you look at the eastern part, the concavity is somehow higher in the south flank of the Churia range. In Dundua range, it has a strong asymmetric pattern of channel concavity. So the south flank has a really high channel concavity compared to the north, as well as the Mohan range is also showing a higher concavity to the south compared to the north flank. And we are also trying to compare the concavity value between its position above the nick point and below the nick point. And we find most of the channel has a concavity higher above the nick point and lower below the nick point, except for Mohan south flank. And we're curious what happened here. So basically I just searched the collinearity from the concavity analysis, where each uh, concavity looking for collinearity of the channel between the upstream and the downstream. And this is the summarize of the summary of those metrics. So if you look at the KSN, it is generally uniform between the north and the south flank. And if we look at here, it goes from the lowest is the eastern Churia. It goes to the Mohan range, and western Churia, and the highest is the Dundwa range. But the Dundwa uh, is showing an asymmetry of KSN. And if you look at the Nick point distribution, so this is a Nick point elevation normalized to base level. So this is in the Western Chura range. We can see that the Nick point elevation to the base level has a uniform magnitude, where it uh, where it goes to Eastern Churia, it's start to slightly shifted on the south flank. So the south flank has a higher concavity elevation to the base level. And in Dundwa and the Mohan range, it is clearly showing a strong asymmetry in nick point elevation to the base level. For the concavity, in Western Churia, somehow it has a higher concavity in north flank compared to the south flank. And in Eastern Churia, Dundwa and Mohan, all the bases concavity are higher on the south flank. So if we're if we're sorting these metrics according to the shortening amount of the structures, so from the lowest here in Western Churia and the highest here in Dundu range, it seems that the KSN has a direct proportional to the shortening amount, as well as the concavity, as well as the asymmetry of nick point and channel concavity. And we also done some normality tests here just to confirm that is actually showing the asymmetry of these metrics between the north and the southern flank. So we can see here most of the nick point, most of the KSN are uniform in both flank, and the nick point, they are asymmetry in the Dundwa and Mohan, and so that's for the concavity it goes asymmetric for all of the ranges. So to explain why does the KSN has a higher magnitude in the south flank of Dundwa range, we are we try to explore at the satellite imagery and using the NDVI images, and we found that most of channels in the north flank of Dundwa range has been backfilled with sediment, which is delineated with the white square here, or the black square over here. We can see it's filled with sediment, so it decreased the KSN of the north flank of the Dundwa Ridge. And for the Western Churia range, as it is uncommon to have the higher KSN or the higher uplift in the tip of the fold, we're trying to explore what happened there. And if we look at the satellite image and the NDVI, it seems that the most of channels in the western part of the Churia range has not been eroded, so it just filled with dense vegetation over here. So I guess so. We guess that the Western Churia, because it's mainly covered by dense vegetation, it's causing the topsoil to act as a highly cohesive layer and resulting in high KSN values within this area. So it is actually a transient signal that the KSN record here to explain the asymmetry of Nick points. We're trying to make this sketch. So if we have a uniform, a displacement between the north and the southern flank, and if the displacement uniform, it will cause Nick point elevation to the base level at the same magnitude between the north and the southern flank, where if if the displacement or the advection of the vertical component of advection is higher to the south, it will cause a higher concavity, oh, higher Nick point elevation to the base level. So I think that uh, so we think that that's actually what caused the asymmetry of concavity in eastern Churia, in Tundwa, and as well as in the Mohan range. So yeah, so the Nick point here will eventually change erosion rates and therefore resulting in higher channel concavity. So we think that the after the concavity, after the Nick point is generated, and it will enhance the erosion in the southern flank. Therefore, it causes a asymmetry in concavity as well. So, oh yeah, so we're going back to this figure. So if we look at the position of the drainage divide uh, relative to the ram position, it looks like as the shortening values increase, so it's from Churi range to the Dunu range, the drainage divide appears to migrate southward relative to the flat ram transition. So it tends to migrate this direction. And the ability of the drainage divide to maintain its position is relative to the fault ram, depends on the erosive capacity of the river network relative to the horizontal displacement induced by lateral rock advection. So we think that what caused the drainage divide migration to the south and the asymmetry of Nick point, as well as the asymmetry of concavity, is the lateral rock advection, which is facing southward in the frontal Himalaya. And yeah, the migration of the drainage divide southward from above the flat ram transition suggests that the horizontal component of rock advection is sufficient to outcompete the erosion in Dunwa and Mohan range. And I also mentioned about the partition of concavity in all these ranges, especially in Mohan. And we tried to explore the role of sediment grain size. So sediment grain size is known to have influence in fluvial network capacity. And Gasparini, in 2004, she found that in a heterogeneous basin, it suggested that the larger grain size tend to produce channel profile with higher concavity compared to the finer grain size. And we are trying to explore with grain size from the backscatter analysis. So we're using a synthetic aperture radar and to measure the roughness of the channel. And what we have here, so it is showing that it has a finding downstream trend. So I guess Laura has a particle grain size study in this basin as well. It's in south flank Mohan anticline, and it is say I mean like well, it's similar as Laura observation with a finding downstream trend. So I don't think that if the larger grain size tend to create a higher concavity, then the Mohan anticline should have a higher concavity upstream and lower concavity downstream. But it's the other way around. It's the opposite. So we think that the grain size is not influencing the partition of channel concavity in Mohan anticline. So we're also trying to explore the bedrock, the bedrock role in defining the concavity within the southern flank of the Mohan anticline. And it match actually. Uh, so the upper stream, the upper reach of the stream is actually underlined by upper Siwalik conglomerates, and the downstream of the stream has a mid Siwalik sandstone underneath, and changes in rock types defines the partition of the concavity as it show here. So in this picture, so here for the concavity point 19, the well, it fits the I mean like the channel, it has a collinearity in upstream, while the downstream all the tributaries are just above the main trunk, which indicating that the concavity is lower in this part. And when we increase the concavity, uh, all the tributaries downstream, it just fit to the collinearity below the nick point. So yeah, I guess that's what causing the partition of the concavity above and below the nick point in Mohan anticline. Um, right, so this is the tectonogeomorphic model that we generated from this work. As, as it shown here, that in Western Churia, where uh, it has the lowest shortening amount, the the anticline is at the initiation phase of the fold propagation fold. Um, and it has this characteristic. So the nick point elevation to the base level is equal for the north and the southern basin, but the concavity is higher in the north, and the KSN is relatively higher to the eastern part of Churia range. And as the shortening increase, as well as the development of the fold propagation fold, the these nick point to base level values shifted to the south flank of the ranges, as well as the concavity. And as the shortening increase, it is getting higher. So yeah, so to summarize, based on the geological cross section, the lowest to the highest shortening across these ranges are the Western Churia, Eastern Churia, Mohan, and then the Mohan, and then the Dondo Ridge. So, and shortening degree correlates with the channel steepness, midpoint distribution, and hence asymmetry of the channel concavity, and the drainage defied migration relative to the fault ram. So, and we assume that the topographic patterns we have found in this study relate to the evolution of the fault system from the initiation of fault propagation fault to later development of the fault, propagation fault, as demonstrated in Denver range. So as the system evolves, the initial symmetrical uplift field, which is demonstrated by the Western Churia here, will transfer into a more symmetrical uplift as demonstrated by the Mohan and Denver range. And greater lateral rock advection relative to the erosion rates drive the asymmetry of the nick point and channel concavity and shift the drainage divide to the fault ramp transition. And yeah, so that's all. Any comments or input?
Thanks for that, Donny. I thought that was a really good overview. I'm going to let other people ask questions because I'm just obviously familiar with what you're doing. So I'll just let other people have a think about this. There's a lot of data, isn't there? A lot of information to consider.
Can I ask something? So
Yeah.
I'm not an expert in any of this, so maybe this is really stupid, but so the fact that the nick points are asymmetric, that's because a movement to the side instead of being completely vertical, right? And because the type of soil is different, is that right?
Yeah.
Oh, yeah, okay. Yeah, I just wanted to make sure because
okay.
Yeah, that's fine.
Okay, thank you.
I have questions, but if other people want to ask first, because I have a lot of questions.
Okay.
Well, not a lot, but okay, shall I start?
Okay.
Yeah, so the first one is about the difference in concavity between the what's above the nick point and below the nick point.
Okay.
How well constrained is it, in the sense, like, what is the uncertainty that you have on the data? Because I imagine, I mean, the segments, they're quite short. So how much variation, like, can you, if you've got a concavity of 0.25, for example, can you say it's 0.25 plus or minus 0.01, or is it 0.25 plus or minus 0.2, which I think is gonna, because I think, you know, the segments are so short that I'm not sure you can resolve that in such a, but yeah.
Okay.
You know.
So at first, so this is actually related to the process on how we extract the best fit concavity on these channels. So, so if we go back to here, so in this case, we're trying to find the best collinearity between the tributaries and the trunk channel. And what this analysis is doing is just, so it's trying to match the concavity from 0.01, 0.0 to 0.003 and going on until it's 1, and until it find the perfect match for this collinearity. And what I did is I'm using those information from the best fit concavity analysis, and trying to matching the best fit concavity for above and the below nick point. So yeah, it's
Just broadly, those box plots are showing that there isn't statistically a difference above and below.
Sorry?
The box plots that you showed on the
yeah.
But the box plot, that's the they show the range of best fit concavity for the different streams. It doesn't show that stream as a concavity of 0.25 plus or minus. You know, it doesn't show the level of uncertainty on the values there.
But you know, though, I mean, those, if you just take those figures as they are, Statistically, there isn't a difference between those between the two populations for most of those. If you were to do a test on whether they are independent populations, because of the overlap, just because of how what's shown. But what you could do, rather than plot the values above and below, is you could plot the difference in concavity in each catchment and plot a histogram of that and see if it's systematic, show the systematic changes. And if that was always in one direction, that would be stronger than comparing the populations of above and below between all catchments. But comparing the pairwise difference within each catchment and plotting a histogram of that would allow you to see if there is a systematic signal.
That's a good idea. Yeah.
Okay.
Cool. And my
just to jump in here and clarify something, Donny has done a Kolmogorov-Smirnov test to see if they're statistically different. That's the next slide.
Okay.
So I mean, we've
but again,
it's statistical test.
Yeah, but again, it's just like it's like you run a best fit, you get your best fit value, you retain that value, and you put that in a population. But it doesn't tell you if that value, like what range of values give you for one channel.
Yeah, each data point does have uncertainty contained within it. So
all right, okay.
You cycle through. I mean, the way we've done that is you cycle through removing tributaries. So you basically you use a few tributaries at a time, and you just do all the combinations of tributaries. So like there's a range of concavity associated with each of those points.
Okay, cool.
Yeah.
Okay, thanks. And
that's not reported. Donny hasn't reported that. Yeah, but
yeah.
I mean, I should also clarify that there is no one else in the world that does this.
I know. I mean, I think this is what you've done is really, really cool. I think that's amazing, Donny. Compared to the last time I've seen that presentation, I think that's amazing.
Thank you.
Yeah, I mean, so I think there definitely is more work to be done on refining these uncertainties, but yeah, I mean, we've tried a lot of different methods to quantify that uncertainty. So
yeah.
Cool.
I'm just going to ask another question. If you go to the last slide, that one. I think I just found it interesting how I'm just wondering whether the difference in lithologies can explain the difference in concavity, because I think in particular on the sketch at the top left, like the way things are drawn almost makes me, I'm wondering whether so on the left, like the channel is cutting through the same rock type, so potentially you would expect like a nice concavity, everything is regular. The top, the eastern choria, just to the right, it's in the blue at the top, and I'm just wondering if that is more resistant to erosion. That means the channel will have to be a bit steeper, which technically would make a channel that is more concave. And it's the same with the bottom left. I mean, I don't know how realistic these things are, but I'm just wondering whether having bits of the channel that cut in a different rock type make them locally steeper. If the channel is steeper near the top, that makes your channel more concave. If it's steeper near the bottom, then it's going to make it less concave. So I'm just wondering whether this difference in lithologies can explain some of the difference in concavities you observe.
Okay, so yeah, I guess it also can explain that. So we try to explore that in this picture here. So yes, as I said before, the upper Siwalik rock has a lower concavity compared to the mid Siwalik sandstone in downstream. So yeah, I haven't looked at that.
Yeah, okay. So I was wondering whether some...
But yeah, but it can actually explains the change of concavity as well.
Okay, so I can see that on the diagram now. I can really see like it's not at all what I was thinking. So okay, thank you very much. But yeah, great job, great work.
Thank you, Mikhail. Anyone else? Or should I just... Okay.
Donnie, having seen this, are the nick points also located at the, because in these images you've shown right here, the nick points seem to be located at the transition between the two rock types.
Yeah, I tried to look for that. So if we look at this cross section, the nick point is actually not located on the boundary between these two rocks. So it's further upstream. So it's located in the upper sea valley conglomerates. That's what I found in Mohanty Mine. So I don't think it's the nick point is caused by the differential rock types. So I guess it's probably due to the uplifting signal.
Okay, super.
Okay. All right.
Any other questions?
I guess one thing I was interested in is just thinking about that divide migration story that you've got there. What you're saying is that I think this is really interesting. So just morphologically, if you think of the area, that the drainage divide starts overlying the ramp where the structure starts to go from a flat to a ramp, and that as shortening continues, that drainage divide migrates. And according to this, if you look at say the Dundwa range, the drainage divide is now about 10 kilometers southward of where you would argue it was initiated, which has interesting implications for the sort of morphology of the dune behind it, the sedimentary basin behind it. Effectively, it means that area is widening, but I suppose it's widening with the topography of the ridgeline. So, and of course, all the maximum sediment is actually being eroded out into the plains as it becomes more asymmetric. Just trying to think what the implications are for that divide migration, if we think that's the case, that you're dividing, that you're migrating the drainage divide significantly southward over time, and what it implies for the northern area.
Oh, yeah. So, yeah. Okay. So I guess it's probably will delivering more sediment to the dune in the northern side of the range.
Yeah, it must be, mustn't it? Yeah, that must be one implication, that the discharge from the dune must increase through time, which you'd expect normally anyway, just with the system growing, but actually with the system growing and with the drainage divide migrating southward, there should be quite a significant increase in the flux from the south.
Yeah.
Yeah, interesting.
Okay. All right. So I'm just going to.
All right. Thanks, Donnie.
Stop sharing. All right. You're
So,
welcome.
Yeah, thanks.
Yeah.
Any other news today?
Maybe just one quick thing. There's that Global Change Symposium that's happening in early December. And I think PhD students were very encouraged to attend. And we've been told that only a third of the Global Change PhD students have confirmed whether they would attend or not. So if you haven't, I don't know who has sent the message. It may be, actually, I'm not entirely sure, but it's a nice, like, there will be an introduction to the new Global Change PhD students. So it's a nice way for each other to learn what we're doing. So yeah, it's probably a good idea to try to attend. When is it?
Have all the first year PhD students been approached independently, or are the supervisors meant to do that, to tell them about that
symposium? I think they have been contacted. That's what the message seems to suggest.
Okay.
There was an email last week that
from Kate Heel.
I don't know.
Or Roddy, maybe Roddy.
But yeah, if you find, you must have received a message, Global Change Symposium, and yeah, if you find it, please try to respond and try to attend, because it should be a fun event.
What date is that? Is it beginning
it's the
December?
2nd
When
or
is
the
it?
3rd of December. Let me check. It's the 2nd of December, Wednesday.
Everybody's frozen on me.
All right. So do we have any ideas for next week? Would anyone like to present next week?
I think Mark has told last time that he has something to present. Mark?
Possibly. I'm just looking because I've got a bit of extra teaching next week. Oh no, it's week 10. That's fine. Yeah, I could say something about what we're doing with the Feshy stuff and what we're looking at doing there.
Cool.
Yeah, that'd be great.
Sounds good.
So I went out of Wi-Fi there. What's the date for the symposium? Is it? I suppose I'm wondering, are we also getting
2nd of December?
Right. Are we going to find an opportunity where perhaps the first year PhD students can present to us more informally before they then present to the symposium?
Yes, we
We
could
can
have
do
an
that the
LSD
week
meeting.
after.
Week
Yeah,
after
we could
next,
do
yeah?
that the week after Mark presents.
Yeah, exactly.
Yeah, in 2 weeks.
So maybe we could all just make sure all first year students, because they're not all here, most are, but that are aware of that, and just do 1 or 2 slides. So I think that's all you get. I think you get something like 2 minutes at the symposium, don't you?
I have no idea.
Usually, because I think there's
Last year we got 1 minute, I think.
there's 30 new students, I think, for Global Change. So it is going to be a rattle through quite quickly. They might even do it in batches.
Anya, did they tell you how long you have?
I can have a quick look actually. It was pretty short.
I think it says 1 slide in 3 minutes, and there's 2 minutes for questions as well.
Oh right, okay.
Yeah.
Wow.
Rapid talking.
Okay.
Yeah, let's do that in 2 weeks' time then. Great.
Sounds
Great.
good.
All right. Good
Well,
to see everyone.
Yeah, good to see everyone.
Take care.
Thanks,
See you again
Donny.
soon.
Yeah.
Bye.
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 Bye.